Hello guys, welcome back to my channel. Today we'll be calculating a crazy integral and I'll try my best to explain all of the steps, and there are a lot of steps. So please don't lose patience and watch the video till the end. Let's get to it. Okay, so we have before us the integral from 0 to pi over 2 of natural log of cosine of x times the square root of natural log of sine of x all over the tangent of x dx. Now, generally in integration, we don't like denominators, so I'll just convert my tangent into a cotangent and then write it in the numerator. The cotangent of x times the natural log of the cosine of x times the square root of the natural log of sine of x dx. Now, interesting thing to notice is, and I'm assuming you know your derivatives really well, that the derivative of the natural log of sine of x is nothing but cotangent of x. So on the same note, let's introduce a substitution. Let u equal natural log of sine of x such that du is nothing but cosine of x over sine of x dx, which can be written as the cotangent of x dx. And yes, we have that, right? So we have a substitution for dx. Now let's take care of this natural log of cosine of x. So we know that e raised to u is equal to sine of x, right? From this. But well, how can we express the cosine in terms of the sine? Well, we know the square identities, right? We know that cosine squared of x is nothing but 1 minus sine squared of x. So cosine of x is nothing but the square root of 1 minus sine squared of x. I'm going to do the same. So sine squared is nothing but 1 minus e raised to 2u, and then the square root of that thing is your cosine of x. Now we just need to take the natural log on both sides, because we had an ln of cos of x. We have the natural log of the square root of 1 minus e raised to 2u. Now everything is raised to the 1/2 power in the argument, right? So using log properties, I can pull the power, I can multiply the entire thing by the power half ln of 1 minus e raised to 2u. Alrighty then, we have our integral now. Half, because of this, integral of square root of u times the natural log of 1 minus e raised to 2u du. Now we need to change our limits, right? So when x is 0, ln of 0 is negative infinity, so u will be negative infinity. U is negative infinity. And when x is pi over 2, sine of pi over 2 is 1, natural log of 1 is 0, so u is 0. These are our limits. Fine. Well, you might say we can't do anything. I mean, even if we were to try integration by parts, it would like really fail. It would be really hard. I mean, I don't think it will work anyways. So we can just use the Taylor expansion of the natural log, because we know that natural log of 1 plus x is equal to the infinite sum. So sum from 1 to infinity of negative 1 raised to k minus 1 times x raised to k over k. So it's some sort of alternating series. So instead of this x, why don't we substitute our e raised to negative e raised to 2u, and we just have the sum from 1 to infinity of minus 1 to the kth power, k minus 1 power, sorry, and negative e raised to 2u, the whole thing raised to k, all over k. Now I would like to clean this up a little. Sum from 1 to infinity of minus 1 raised to k minus 1, and then we have a negative 1 raised to k, right? So I can add it plus k with this negative 1. We have e raised to 2uk over k. Now I would like to just separate this a little bit. So k goes from 1 to infinity, minus 1 raised to 2k, right, times the negative 1, because raised to, you can say, negative 1 power, e raised to 2uk over k. Now the best part over here is negative 1 raised to an even number, right? So because k is from 1 to infinity, 2k is always an even number. So negative 1 raised to an even number is always 1. So this will just be 1. This will be negative 1. So finally we have negative sum of from 1 to infinity of e raised to 2uk over k. Now what was our integral? Well, our integral that was left to evaluate was half integral from minus infinity to 0 square root of u natural log of 1 minus e raised to 2u du, right? And then we obtained a term for this natural log. So I'll just like to plug everything in now finally. So we have half integral from minus infinity to 0 of negative root u infinite sum from 1 to infinity of e raised to 2uk over k du. And now because there is an uniform convergence, we can just interchange uh, the infinite sum and the limit. So I'm going to take the all the sums which all the terms which do not depend on u out of the integral sign. So I have negative infinite sum from 1 to infinity of 1 over 2k times the integral from negative infinity to 0 of square root of u e raised to 2uk du. Now, this is a very cumbersome expression. We can't use integration by parts again. But looking at this is makes me think about the gamma function. And I hope you remember what the gamma function was. So say the gamma of say a number k prime in our case, nothing but the integral from 0 to infinity of e raised to minus y raised to k minus 1 dy. So only thing we need to do over here is somehow change this 2uk to like a negative number, and then we might get get this form. So let's try and do that. Let's introduce a substitution. Let 2uk equal negative w. So u is nothing but negative w over 2k, differentiating with respect to u on this side. So we have 2k du is equal to a negative dw. In other words, du is equal to negative dw over 2k. Now I want to just substitute everything over here. So there was already a negative. That negative will get nullified by this negative of the du substitution. So we'll just have sum from k equals 1 to infinity of 1 over 2k times the integral from, we'll check for the limits later. So square root of u is nothing but square root of negative w over 2k times e raised to negative w dw. So when u is negative infinity, w is infinity. When u is 0, w is 0. So there we go. Now I would, since the in the gamma function we had the integral from 0 to infinity, we have here an integral from infinity to 0. So I would like to flip this thing by putting a negative sign in front of it. Sum from k equals 1 to infinity of 1 over 2k. Well, I forgot the 2k of the dw, sorry for that. Times yeah, 2k again, and then this we can pull this square root of 2k outside, and inside we have the integral from 0 to infinity. Now we, as I said, we flipped the limits by introducing this negative outside. This is a square root of negative w e raised to minus w dw. Let's clean this up a little bit. Sum from k equals 1 to infinity of, this is 4k squared, 4 root 2 actually, k squared times root k, and we have square root of negative 1 inside times square root of w, so we can pull the square root of negative 1 outside and call it I, because it's an imaginary part. So integral from 0 to infinity of w raised to half e raised to minus w dw. Well, what does this look like? Comparing it to a gamma function, this is nothing but the gamma of 3 by 2, because there was the argument minus 1 for in the on top of the w. So in our case it was y, but it was argument minus 1. So 3 by 2 minus 1 is integral 1 by 2. So this is nothing but the gamma of 1 by 2. But we still have the other part to calculate. So sum from k equals 1 to infinity of I upon 4 root 2 k to the 5 by 2 power times the gamma of 3 by 2. Now we can just indeed clean this stuff by rationalizing the denominator, multiplying and dividing by square root of 2. We have sum from k equals 1 to infinity of I root 2 over 8 times k to the 5 by 2 power and the gamma of 3 by 2. Well, what does this look like? What is the sum from k equals 1 to infinity of 1 over k to the 5 by 2 power? Well, that is nothing but our Riemann zeta of 5 by 2, right? Because what was Riemann zeta? It was the sum from k equals 1 to infinity of 1 over k to the s. That was your Riemann zeta of s, so as to say. So we know these facts. Indeed, this is negative I times root 2 over 8 times the Riemann zeta of 5 over 2 times the gamma of 3 by 2. Now we can find the value of the gamma of 3 by 2. So this could be another video, but I try to do it. I like to do this quickly over here. So we know the gamma of, say, z plus 1 is equal to z times the gamma of z. So the gamma of 3 by 2 is nothing but half times the gamma of half. And so we have a half like that, and let's plug this into the definition of the gamma function. E raised to minus, let's take y now, y to the negative half dy. Now I want to convert this into somehow a Gaussian integral. So I'll let y equals v squared. So dy is equal to 2v dv, and y raised to negative half power is nothing but 1 over v. We can write everything finally as this becomes e raised to minus v squared over v, and then dy is 2v dv. Now our limits, let's check our limits. So when y is 0, v squared is 0, y is infinity, v squared is infinity. So limits remain the same. Well, great part is the v's cancel out, the 2's cancel out. We're only left with what we sought to put the original integral in the form of the Gaussian integral, e raised to minus v squared dv, right? This is the Gaussian integral. And what's the value of that? Well, square root of pi over 2. I'll probably do the proof of this in like another video. Well, that's great, right? So we have a value for the gamma of 3 by 2. So minus 1 times root 2 over 8 times square root of pi over 2 times the Riemann zeta of phi over 2 minus 1 times square root of 2 pi over 16 times the Riemann zeta of phi over 2. Well, yeah, I mean, we can't, I won't go ahead and put like a value for this. It's Riemann zeta of phi over 2 is like really complicated, and I don't think there's like a legit number also. So I mean, who would have guessed like that this simple integral would lead to an imaginary answer? I mean, all of this is imaginary, right? Because of this I, everything, like the real component is like 0, and then this is like the imaginary part of it. So I guess that's it for this video, guys. I'll be posting some more videos. I don't know, I'll just probably do more sums like these. So stay tuned. Have a great day. Bye.